Alice and Bob take turns picking up whole piles of stones from either end of the row, with Alice going first, and each of them always tries to end up with more stones than the other. There's an even number of piles, each holding some positive number of stones, and the total is odd, so the game can never end in a tie. Beginner level. 2 players take turns picking up piles of stones. But here's the catch. On every turn, you can only grab the pile at the far left end of the row, or the pile at the far right end, never from the middle. The wild part is that one of these two players literally cannot lose, no matter how well the other one plays. Try to guess which player that is before I tell you. Imagine splitting a jar of candy with your sibling, one piece at a time, and you can only take from one end of the row of candies or the other. Whoever thinks ahead ends up with more, even if the pieces look about the same size. That's exactly the shape of this problem, and it shows up again and again in interviews under different names, so it's worth learning properly once. Let's make this concrete with numbers. 5, 3, 4, 5 stones in a row. Alice goes first, and her only two choices are the 5 on the far left or the 5 on the far right. Nothing in between. Then Bob takes his turn on whatever's left, also playing his best. We want to figure out, if both play perfectly, who ends up with more stones. We're going to use a 2D list, basically a grid, like a spreadsheet, with one square for every possible continuous slice of the pile row, piles 0 to 0, piles 1 to 2, piles 0 to 3, and so on. We'll fill it in starting with the smallest slices and working up to bigger ones. And at every square, all we ever do is call Python's built-in max function to keep whichever of two numbers is bigger. For example, max3700 choose 00 just gives you 7. That's give us 0 kit, 0 0. That's genuinely the entire toolkit for this problem. Nothing fancier than a grid and a comparison. The most natural first idea is brute force. At every turn, try taking the left pile, try taking the right pile, and repeat that for every future turn too, like exploring every possible way the game could play out. It gives the correct answer eventually. The problem is that every single turn doubles the number of possibilities you're tracking, so this gets unbelievably slow as soon as you have more than a handful of piles. Here's the key idea that unlocks this whole problem. The total number of stones on the table never changes. It's always 5 plus 3 plus 4 plus 5 no matter who takes what. So instead of tracking Alice's exact stone count, we can just track the difference, her stones minus Bob's stones. If that difference or gap ends up positive, Alice comes out ahead. This one shift is what makes the rest of the solution work. Now let's define what goes in each square of our grid. DPI-GG means if only the piles from index I to index J were left on the table, and it's your turn, what's the best gap you can guarantee for yourself? We'll figure this out for tiny slices first, like a single pile, and build up to the full row, which is DPI0 nice. 1. Let's slow down here, because this is the one idea the whole solution hinges on. On any slice of piles, you have exactly two choices. Take the leftmost pile or the rightmost pile. Say you take the left pile, you gain its value. But now it's the opponent's turn on what remains, and they'll play their best too. Which means from your perspective, whatever gap they achieve counts against you. So your total gap from that choice is the pile you took minus the opponent's best gap on the rest. You do the same math for taking the opponent's best gap on the rest. You do the same math for taking the right pile, then simply keep whichever of the two choices gives the bigger number. That's the move of smart player. The simplest possible slice is just one pile by itself. If that's all that's left, you take it and your gap is exactly that pile's value. That's our starting point or base case. Every bigger slice's answer depends on smaller slices already being filled in first. Since the trick from the last slide needs DPI plus 1 JJ and DPI plus 1 JJ to already exist. So we fill the grid by increasing slice length. All length 1 slices, then all length 1 slices, then all length 2 slices. First, zeros to n for b in range in the list is a list comprehension that builds a grid of n rows and n columns, all filled with 0. That's our empty table. Then the loop fills in the base case from the last slide. DPI each is the slice containing only pile I. So its best gap is just piles I itself. The outer loop walks length from 2 up to n, so we always tackle bigger slices only after the smaller pieces are already filled in. For each length, I is where the slice starts and ji plus length 1 is where it ends. Then we apply the trick from before, piles ai, dpi plus 1, jij is the score from taking the left pile, piles aj is the score from taking the left pile, piles ajjj, dpijj1 is the score from taking the right, and max keeps the better one. At the very end, dpijjjj and 1 1 force the best gap for the entire row. If it's greater than 0, Alice wins. Putting it all together, we build an empty grid, fill in the single file base case, then sweep through increasing slice lengths, applying the same left versus right comparison every time, and finally check whether the whole row's gap came out positive. Let's trace through the actual numbers by hand. So you can see the table fill in for real. The singles are just the piles, dp1 series cdp2 cdp2 series series cd3 cd5. Now length 2, dp0 series 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 c2 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 series 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 c2. Take light is cdpt0 series c2 to tdpt0 series 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 cd 2 2 series 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 cd. First series 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 cd. First series 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 45 40 series series with zeros covers in CD. Take left is 40 series series series, so it's 4 dpd series series 40 series 40 series. So now it's your turn to practice. Grab a pen and try piles 3 7 2 3 using the exact same steps. Fill in the singles, then the pairs, then check the whole row. Pause the video here and work it out before I show the answer. Doing it yourself once is what makes this stick. The first time I wrote this, I looped through I and j in plain top to bottom order instead of by increasing length and got garbage answers. That's because the recurrence needs dpi plus 1j and dpijjp filled in to already be filled in. And if you fill by row, you'll sometimes read a square that's still 0. Second mistake, trying to track each player's raw stone count instead of the gap between them. The subtraction trick only works with the gap. Third, writing range 2 and instead of range 2 and instead of range 2, n plus 1, which quietly skips filling in the full row and gives you a wrong final answer with no error message. For piles 3 7 2 3, if you placed it correctly, the table still comes out positive. Alice wins there too. Here's a fun twist. For this exact problem, you don't even need the table. Notice the piles split naturally into two groups. The ones at even positions 0, 2, 4 and the ones at odd positions 1, 3, 5. It turns out Alice can always force herself to take every single pile in whichever group she picks, just by always responding to Bob's move with the matching end. Since the total number of stones is odd, those two groups can never be equal. One is tricky bigger. So Alice just picks the bigger group at the start and wins, always. The catch, this only works because the problem guarantees an even number of piles and an odd total. Change the piles first like in later versions of this problem, and this shortcut breaks. The ones at fourth place can never piles move. The ones at a DP grid has roughly n times n squares, so both its time and memory usage grow quadratically. With 500 piles, that's around 250,000 squares to fill. The parity trick, by contrast, is just one check that takes the same tiny amount of time no matter how many piles there are. Use the DP approach when you want reasoning that still works if the rules change. Use the shortcut only when you've confirmed these exact conditions. Even count or total hold. With just 2 piles, the table is tiny and the answer is obvious. Alice takes whichever pile is bigger, and since the total is guaranteed odd, the 2 piles can never tie. Even with the largest allowed input of 500 piles, the quadratic table is still fast enough to run instantly. And because the pile count is always even, the base case always has a clean match with no leftover pile. Remember that guaranteed win claim from the very start. You've now proven it 2 completely different ways. The interval DP, where we reframe the game around maximizing your score gap and fill the table's smallest slices first, and the one-line parity trick, which works specifically because of this problem's exact rules. This same DP pattern reappears in Stone Game 2 and 3, where the rules shift just enough that the shortcut no longer applies and the DP becomes your only tool. If this clicked faster than you expected, a like helps a lot.